Okay, this is 5.3 exponential functions, and today's objective would be to define and use exponential functions. Seems pretty straightforward. Define them and use them. Okay, so first off, the general form of your typical exponential function, and I want you to think about simple interest. I know we have two forms as of yesterday, but let's go back to simple interest right here. And that's simply going to be f of x equals your initial value, which we like to call a, times your growth factor, which we can call b, to the x power. Okay? So, now your base b is your growth factor. Like in the simple interest formula, that b is 1 plus the growth rate, 1 plus r. All right? So, let's think about what's going to happen if b is greater than 1? Well, do you remember our $4 hamburger? Okay, that $4 hamburger had a b, or a growth factor, of 1.09. All right, so that's going to be exponential growth. Now, what if our base, or our growth factor, is between 0 and 1 exclusive? And that's the situation of my truck. All right, I forget, what was my truck? We were having a growth rate of negative 20%. Oh, that's depressing. So in that situation, we're going to have exponential decay. So now, what do these look like? Well, again, for the hamburger, the $4 hamburger, the y-intercept was 0,4. It's just that a right there. So your initial condition a is your y-intercept. So here we have 0, a, and over here we also have a y-intercept of 0, a. Okay, and this a over here was $8,200 if I remember right. But because our growth factor b is greater than 1, here 1.09, we have exponential growth. And over here, where, what was that again? 0.8, I believe, was my growth factor, which is a number between 0 and 1 exclusive. So that would be exponential decay, which always looks like that. So there's your typical exponential functions right there. Exponential growth, exponential decay. A is always your y-intercept, and when b is greater than 1, your growth factor is greater than 1, you have exponential growth. And when your growth factor is between 0 and 1 exclusive, you have exponential decay. Now, let's talk domain and range of your typical exponential functions. What's the domain? Well, my x values over here are going to go forever and approach, towards negative infinity. All right, the same thing, I'm going to go forever to the right, towards positive infinity. And that's the same whether we're talking about exponential growth or exponential decay. So the domain of these exponential functions would be the set of real numbers. Now, what's the range? Well, again, both of these graphs, as x approaches negative infinity over here, f of x is getting closer and closer to the x-axis. So we are going to stay greater than 0. Over here, the same thing. As x approaches positive infinity, y is going to get closer and closer to the x-axis, but never quite reach it. So the range would be, you could say this in two ways. You could say the positive real numbers, that's an r with a superscript of a plus, or just say y is greater than 0. Okay, exponential functions. Okay, different forms of exponential functions. Exponential functions. Remember, y equals a times b to the x power. All right, well, we have already studied simple interest. All right, and that simple interest is nothing more than a of t. Well, see this a? When we're talking simple interest, we like to call that a sub 0, the amount we're investing initially. And see the base right here, that's our growth factor. We like to call that 1 plus r, because then we have 1 plus our growth rate. And that would be to the t power. Now one more time, let's write down what these parts are. So a sub 0 is our initial amount at time t equals 0. And what is that r? That is a growth rate. And a lot of people, they confuse growth factor, which is the entire parenthesis, and growth rate. And I do that too. I know what they mean, but sometimes I call them, I mix it up a little bit. Okay, I've been known to call the growth factor a growth rate. And the 1 plus r is a growth factor. R is your growth rate. Okay, know the difference between the two. Okay, now our next form. Well, the next form of an exponential function we use a lot in science. And that's our old half-life or double life formula. All right, and it looks like this. A of t equals a sub 0 times b to the t over k power. A of t equals a sub 0 times b to the t over k power. All right, so you have your initial amount again, and then you have this growth factor, but the growth factor is not to the t power, it's to the t over k power. All right, so what's that k about right there? Well, k would be the amount of time it will take to multiply a sub 0 by b, because let's say t is 5. If k is 5, 5 over 5 is 1, and b to the first power is b. So I get a sub 0 times b. So k, time needed to multiply a sub 0 by b. All right, so what we're going to develop in this lesson today is your ability to take a story problem and put it into one form and then convert that form to the second form. So you take what they give you to determine which form you're going to start with. So a bank advertises that if you open a savings account, you can double your money in 12 years. I'm doubling my money. Half/double life, I think I'm going to use form 2. Okay, so that's going to be a of t equals a sub 0, and I want to double my money, so that's going to be my growth rate, b, or my base. Double it, and then what's my k? Well, I'm going to double my money in 12 years. So that's going to be 2 to the t over 12 power. All right, and there you go. There is my double life formula right there. Now, can I convert that to my simple interest formula? Well, use form 2 to come up with the growth factor. Okay, so the growth factor. Well, I need to come up with a 1 plus r. Okay, can I manipulate this so I get a 1 plus r quantity to the t power? You betcha, with laws of exponents, and here's number 7 again. Power of a power, b to the x to the y equals b to the xy. So this is a simple manipulation right here. Okay, I need 2 to the t over 12 to be written as 1 plus r to the t. Well, 2 to the t over 12, in form number 1, I just need an exponent of t. So there's my t out there, but what have I not accounted for? The 2 to the 1/12. Again, b to the xy equals bxy to the xy. So this 2 to the 1 over 12 to the t equals 2 to the t over 12. I just multiplied the exponents, x times y. 1/12 times t is t over 12. All right, now guess what this 2 to the 1 over 12 is? That's my 1 plus r. So now let's just punch that out on a calculator. 1 plus r equals, well, what's 2 to the 1 over 12? I punched it out and I got a of t is approximately my initial amount, a sub 0, and 2 to the 1 over 12. When you punch that out, make sure you put that 1 over 12 in parentheses, and I got 1.059 as a growth factor. Okay, now I can leave this like that, but if you want to go the form 1 plus r so you can clearly see your growth rate, you could rewrite it like that. That equals a sub 0 times the growth factor of 1 plus my growth rate of 0.059. Okay, so that's what you're going to do. You're going to get a story problem where you can clearly use one of the forms of your exponential functions and then be able to convert to the other form. All right, the rule of 72. This is big. If a quantity is growing at r% per year, or maybe your time is in months, then the doubling time is approximately 72 divided by r in years or months, depending on your unit in time. So, let's think about that last problem we were looking at where we had a of t was equal to a sub 0, our initial investment, times the growth factor of 1 plus 0.059 to the t power. Well, our growth rate right there was approximately 6%. So, if I want to figure out approximately how long it's going to take for my investment a sub 0 to double, wouldn't that a sub 0 look really good if it was 2 times a sub 0? All I use is the rule of 72. So I'm going to go 72 divided by 6 equals, and that's a 12. So guess what? If I'm making 6% simple interest, it's going to take approximately 12 years for my money to double. At a rate of 6%, it will take about 12 years to double my investment. Wow. All right. Now, I took that into account when I borrowed money too, like for a mortgage. All right. I had a 30-year mortgage, and I was thinking about things like the rule of 72 and the bank getting all of that interest from me. So I converted it to a 15-year mortgage and even lowered my rate. And, I'm about to pay that mortgage off any day now. So again, this kind of stuff can really impact your future financially. Okay, last story problem right here. A radioactive isotope has a half-life of 5 days. At what rate does the substance decay every day? Well, I'm going to start with, I see half-life. So how about if we start with our half-life formula, which is a sub 0 times b to the t over k power. All right, and I write these formulas down every time I use them. Okay, now let's put in what they gave us. So that equals, they didn't tell us how much radioactive isotope we started with, so that's going to be a sub 0, but we are talking half-life, so b is 1/2. And then to the t over k, which is the amount of time of that half-life, that's 5 years. So there's my formula right there. Great. Now, at what rate does the substance decay every day? Well, I can't see this here, but now if I went to simple interest, all right, which remember is a of t equals a sub 0, okay, times 1 plus r to the t power, that r right there would be my daily rate. So let's convert a sub 0 times 1/2 to the t over 5 power to a sub 0 times the quantity 1 plus r to the t power. That means I need to use my laws of exponents to rewrite this part right here with a power of t out front. So convert the second form to the first form. So a of t equals, all right, well, we have our a sub 0, and notice I left the power of t out there. That means by the laws of exponents within this bracket, these grouping symbols, wouldn't I have to have 1/2 to the 1/5 power? Now, do you guys all agree that 1/2 to the 1/5 to the t is 1/2 to the t over 5 power? There we go. Now, all I need to do is punch this out on a calculator. So a of t is approximately a sub 0 and 1/2 in parentheses to the, make sure you put this 1 over 5 in parentheses, that power, and my calculator gave me 0.87. So can I see at what rate does the substance decay each day? Well, it looks to me like I'm decaying at 13%, but if you don't see it in this form, let's rewrite this 0.87 as 1 plus r. So a sub 0 times 1 plus, and I need 0.87, so that'd be negative 0.13. Negative 0.13, and there is my growth rate. That's actually a decay rate. So I'm going to answer this question like this. Therefore, the daily decay rate is, so I said decay, so I don't need that negative. It is 13%. And there you have it. All right, get really good at using your two forms of exponential growth or decay and converting from one form to the other using laws of exponents. So I would like you guys to do section 5.3, 1 through 21 odd, and then number 25. You guys have a great day.